In this session, we are going to discuss about the mass transfer correlations in this mixer type or in a mixer of this mixer-settler extraction system. So, in the previous session basically we have discussed about the different numbers which are used basically in the development of the mass transfer and different other correlations. So, the list of these dimensionless numbers which are important for different correlations, that's of practical importance in liquid extraction process. So, these are to be again extended, right. We have discussed about the Froude number, Reynolds number, Weber number, Bodenstein number, Galileo number, right. And there is also some another one. So, that is called the Yodvorst number, which will be used in this correlation, the empirical correlations for the continuous phase mass transfer coefficient. So, let us again have a discussion regarding these numbers, because the correlations actually we do not have to remember, but these numbers are important and their physical significance of course. So, let us list the numbers. Important dimensionless numbers in liquid extraction, and specifically in mixer-settler system, right. So, you see that we have the Froude number, sorry, first it is the Weber number, WE, that is inertial force by force of interfacial tension, and this will be equal to rho V square L and sigma into L. So, it is rho V square divided by sigma, right. And you see for the present system V is equal to pi Ni di, where Ni is the RPS and di is the impeller diameter of this mixer. So, we get Weber number for the present system, pi definitely we drop. So, rho Ni square, this di square divided by this sigma. Oh sorry, this will be L square. So, this will be L. So, here it will be di cube divided by sigma. Next, Froude number for continuous phase, or Froude number in general. This is gravitational force or inertial force by gravitational force. So, inertial force is again rho V square L square and gravitational force is rho L cube G. So, it is V square divided by L G, that is the Froude number. So, Froude number for continuous phase, here we have two different Froude number. One is Froude number for continuous phase, that is Ni square di square divided by di into G, which is Ni square di divided by G, right. And Froude number for the mixture, here we multiply this Ni square di into G will remain same. Here we multiply it by rho of m, rho of mixture divided by delta rho. Now, what is the rho of mixture? the rho of mixture is equal to phi into rho d plus 1 minus phi into rho c, where phi is the volume fraction of dispersed space. Right? Phi is the volume fraction of the dispersed space, and rho d is the density of dispersed space, rho c is the density of continuous space. And definitely delta rho is equal to rho d minus rho c mod, the difference. Okay. Next it is, so this is about the Froude number. Next it is Galileo number. See, in previous session we have stated that this is bound force into this inertial force by viscous force square. So, it is very similar to the not exact to this Grashof number what we have used in heat transfer, right. So, bound force you see, or here it is I think it is the net bound force, right. So, net bound force is delta rho into L cube into G, but net bound force is bound minus gravity. So, multiplied by rho V square L square divided by mu into V by L into L square whole square. So, that becomes this delta rho, this L square here, delta rho into L cube into G into rho divided by mu square, right. Yeah. So, for extraction this Galileo number is defined as delta rho, it will be as it is, this is di cube into G, and here this is rho mixture divided by mu mixture. Okay. Now, mu mixture square, sorry. So, mu mixture has got an empirical rule by which we can calculate. So, this is mu c divided by 1 minus phi. How we have got it, we are not going into that. It is purely physical combined with statistical analysis, that what sort of average we should go for in order to get correct relation, right. So, this is the mu mixture, we have to substitute here, we do not have to remember this correlation. So, actually in book you will find that it is the net bound force or the bound force by viscous force only, right. So, this is in the order of bound force, it reduces to actually divided by viscous force. Why? As Reynolds number is in the order of 1, and Reynolds number is what? Reynolds number is inertial force by viscous force. So, inertial and one viscous force cancels out, giving bound force by viscous force as the significance of Galileo number. Okay. So, next is Bodenstein number. Bodenstein number is bound force by force due to a net bound force divided by force due to interfacial tension. So, net bound force in general we can write that delta rho into L cube into G. So, this becomes delta rho into L square into G divided by sigma, right. So, here this Bodenstein number for liquid extraction BO, it is delta rho into di cube di square into G divided by sigma. So, Galileo number, Bodenstein number, next impeller Reynolds number. That we must discuss, or in general Reynolds number. Its inertial force, as we have discussed in fluid mechanics, by viscous force, rho v square L square inertial force, and mu v by L into L square. So, it is rho v L by mu. And impeller Reynolds number whether I have used any notation, yes, REI, we can also write RE, right. So, it is di square into Ni into rho by mu. Because the characteristic velocity is pi into Ni into di, so this is capital. So, we have got the impeller Reynolds number expression as di square into Ni into rho divided by mu. So, next is power number. So, it is similar to drag coefficient, right, or physically, rather we should write physically same as drag coefficient, and drag coefficient, you know, the drag force by this, or in the order of rho v square L square, half we drop. Now, the force we can write as power by velocity into rho v square L square. So, this becomes P divided by rho v cube L square. So, it is P. Now, pi v cube, we are using the same expression here, but pi will drop. So, rho into Ni cube into di to the power 5. So, that is the power number, okay. And same will be this expression is basically for impeller or this mixer settler. And last is Yoth-Vos number, EOT VOS, Yoth-Vos number. So, that is gravity divided by inertial force, right. So, Yoth-Vos number is gravity force by inertial force, but this is based on dispersed phase, right. So, in general it should be L into L cube into G into rho divided by sigma into L. So, L square G rho divided by sigma. And here, as it is based on dispersed phase characteristic dimension is not the impeller diameter, but rather it is the average diameter of the drops. And average diameter of the drops, we know that we express it by Sauter mean diameter. So, this L square will be D32 whole square or D32 square into G into rho d and sigma, right. So, that is Yoth-Vos number EO, I think, yeah, EO. So, these are the dimensionless numbers which are important for liquid-liquid extraction study in a mixer-settler system. So, we have discussed some of the correlations, the physical correlations like Sauter mean diameter we have expressed as a function, we have discussed it as a function of this Reynolds number, right, sorry, not the Reynolds number, VI has got a relation with this mu d Ni di divided by sigma, this we have discussed in the previous session. and the minimum impeller speed related to the Froude number of the mixture, and that is the dependent dimensionless group, and it has been correlated to Galileo and Bodenstein number along with the volume fraction of the dispersed phase, tank diameter to impeller diameter ratio. Next, the power consumption. As a system, we know that it operates in the turbulent regime, which is marked by Reynolds number greater than 10 to the power 4. So, there the power number becomes independent of the Reynolds number and assumes a value of nearly 5.7 for this typical mixer tank, right. So, that was the last topic we have discussed in the previous session. So, now we will be focusing on the mass transfer correlations. You see that mass transfer coefficient here we have two resistances in series. One is the dispersed phase resistance, another is the continuous phase resistance. So, if I know the dispersed phase mass transfer coefficient and continuous phase mass transfer coefficient through these exact correlations, applicable correlations, and we know the equilibrium relation, right. So, you can apply the interface mass transfer theory, and therefrom we can generate the overall mass transfer coefficient based on dispersed phase or continuous phase, whatever is necessary, right. So, first we will discuss about, so it is mass transfer correlation. First we will discuss about the dispersed phase correlations. Now, dispersed phase correlations we will not go into the broad elaborate type. Here we will go for a simple, very simple correlation which was introduced by Froude in this year of 1963, and correlation, this is correlation proposed by Froude in 1963 for dispersed phase, right. So, here this correlation is specifically valid for a upper threshold or a upper threshold of a droplet size, right. If if the Sauter mean diameter is less than 1 millimeter, there is no convective transport in the dispersed phase. It is rather purely a diffusive transport. Right. Now, when it is a diffusive transport, which is valid for this drop diameter or bubble diameter, it is also applicable for bubbles, the bubble diameter less than 1 millimeter. Additionally, there is another constraint, see, sigma should be less than 15 dyne per centimeter. There is an upper threshold of this interfacial tension. So, these two conditions must be satisfied. So, here the drops are referred as rigid drops. What does it mean? As there is no convective transport, these drops behaves like that of particles of solid, where we can only have solid diffusion, and here it is just like liquid or gas diffusion, so if it is a gaseous bubble or a liquid drop, right. So, these drops are called rigid drops, and for rigid drops the Froude's correlation is valid. Froude number for dispersed phase, which is Kd into d32 divided by dd is equal to 6.6 only, right, where Kd is the mass transfer coefficient of the dispersed phase, d32 is the shorter mean diameter, and capital D is the diffusivity of the solute in dispersed phase, right. For larger drop size, there are correlations, numerous correlations are there proposed by Scaland and ZM. Yeah, it's around this 1990 you will get lot of correlations proposed by Scaland and ZM, and for which are valid for these drops having a diameter, the drop diameter greater than 1 millimeter, right. But these relations are complex. We will show some examples, and similar complex correlations are also exist for continuous phase. I will just write one. Okay. So, this we have to note, where this dispersed phase mass transfer coefficient and the respective Froude number attains a constant value. Okay. Now, continuous phase correlation. Now, this continuous phase correlation, see, this is Scaland and Moiety, this is one correlation. Proposed in 1990 also, this is probably in the same paper, I do not remember exactly. So, this states the Froude number for continuous phase, which is Kc into D32 divided by Dc, right. So, that is, this is a complex correlation, you do not have to remember it, just I am giving the example, 1.327 into 10 to the power minus 5 into Smith number to the power 1/3. Smith number will be equal to mu divided by rho C divided by dc, right. Froude number for continuous phase already we have stated, to the power 5/12 into Yotvos number to the power 5/4, then volume fraction of the dispersed phase to the power minus half, Reynolds number to the power 2/3, then di impeller diameter divided by d32 whole to the power 2 multiplied by d32 divided by dt tank diameter whole to the power half, right. So, this is quite a complex relation and obtained via experimental investigations, experimental results followed by multivariable statistical analysis, and you see that once you have got, see from this analysis what you will get finally Kd and Kc, and my equilibrium relation, let us say it is x prime is equal to m into y prime, where x is the mass fraction or mole fraction whatever in this continuous phase, yeah, x is equal to, or in this raffinate phase, and you have to choose which one is raffinate and which one is this extract, right, and this is in extract phase. Now, generally the dispersed phase, generally it is not the universal rule, generally the dispersed phase is the solvent and the continuous phase is the solute, or this is the carrier, right. It may be reverse and accordingly we have to change. So, 1 divided by KOD, this is the correlation, the overall mass transfer coefficient based on dispersed phase concentration difference, and definitely it is equal to 1 by Kd plus m prime divided by Kc. It is very similar to this interfacial or interfacial mass transfer, right. So, this is the overall idea of how to calculate the mass transfer correlations or mass transfer coefficients, right. And from this mass transfer coefficients, we can write down steady state material balance, and we can go for calculations of these transients, how the concentration in a mixer settler is changing with time. So that's a different issue altogether. We are not going to right now, we are not going into that discussion. So next is, see this what I have mentioned here, it is a dispersed phase and it is a kind of drop which is called rigid drop, right. So in rigid drop, diffusive transport is only transport. Now if the drop size increases, and for which we have this Scaland and GM correlation that I have not cited here, okay. So definitely there will be convective mode of fluid, right. So how this convective mode is being generated, or whether there are any other influencing factor that actually dictates the rate of mass transfer. Yes, there are two specific phenomena we have to consider, right. So dispersed continuous mass transfer is heavily influenced by a set of factors, and phenomena, right. Two most important phenomena are, number one, internal circulation, and number two, Marangoni effect. So you see, what is internal circulation? When a drop, liquid drop of size greater than this 1 millimeter moves through a pool of liquid, it displaces the liquid, and liquid is also being continuously churned, right. So liquid locally will have a streamline, there may be eddies and all. So because of that, internal to the drop, we have a circulations like this, okay, because at this interface we have this tau r theta, or rather it is r phi, right, of dispersed phase is equal to tau r phi of continuous phase. R is the direction, see over here, r is the normal direction and theta is the tangential direction. So area is this norm follows the normal direction, that is the direction of r, and according to the spherical coordinate phi, the polar angle, it's just follows this longitudinal circles directions. So it is downward, right, it's tangential, okay. And also we have the shear in this direction as well. So we can write this tau r theta dispersed phase is also equal to r theta continuous phase, where theta is the azimuthal angle, okay, according to the choice of the spherical coordinate. So as a consequence, where the shear stresses on the dispersed and continuous phases are same, so the content or the fluid inside the dispersed phase, that is also subjected to that shear, and it will evidently will set in motion if the drop size is above and over 1 millimeter, right. And as a consequence, there will be a convective current setting inside the drop, and the mass transfer and this dispersed phase mass transfer coefficient is heavily increased. So internal circulation is a phenomena which heavily influences the dispersed phase mass transfer. Now on the other hand, see, we have a solute being transported from dispersed to continuous or vice versa. So as a consequence, we may have the effect which was originally proposed by Marangoni, and it's called Marangoni effect. What is it? See, if this is the interface, then actually we have to understand that interface is 2 to 3 atom thick, right. So, actually this is the interface in the molecular scale. Now, a solute is being transported, let us say, from this side to this side. So, what will happen? Here we will have a higher concentration of the solute, the concentration gradually drops, right. So, if this is the x direction, we have dc dx, right, not equal to 0. There will be a dc dx close to that, or over the across the interface we have a dc dx. So, once we have a dc dx and this interfacial tension, you see it is a function of concentration, it is a function of solute concentration. So, as a consequence we will have d omega d, d sigma dx, right. So, that is called an interfacial tension gradient, right. So, because of this interfacial tension gradient, the one layer starts moving over another, and it even may result in interfacial turbulence, which severely enhances the mass transfer rate. Okay. Leading to interfacial motion and even turbulence, right. So, what is the effect? The rate of mass transfer increases. So, you see this rate of mass transfer severely increases because of internal circulation and Marangoni effect. So, these two phenomena, at least from the physical standpoint of view, we have to know, right, in order to think about the appropriate correlation to find out the mass transfer coefficient, right. So, that is all about liquid-liquid extraction. So, now we are going to start this another very important chapter of mass transfer, where from we had several gate questions and it is being asked every year, that is drying. So, drying conventionally, we think that okay, I have a solid and which we are reducing in terms of its moisture content. The moisture content of the solid is being reduced through this drying process. So, you see that may not be the case, drying. So, we can have a wet solid, we can have a slurry, or even a solution, right, and we keep it in contact with drying gas. It is thermal contact, it may or may not be having physical contact. So, we can have direct or indirect contact. Right, and it must produce what? A dried solid. Okay. It must produce dried solid and solvent vapor, mostly water, and solvent vapor is transported or entrained by the drying gas stream. So, this is classically what we refer, or technically what we refer as drying process. Okay. you can have any sort of feed. It necessarily is not a solid, it may be a slurry, it may be a solution. And we must use the utility of drying gas or drying medium, right. So, there must be a flow of some gas, okay. So, or rather we should say it is not a drying gas, it is a drying medium, right. So, drying medium may be the gas itself, or we can have the indirect drying, like we can place a solid over a hot surface and there is a flow of cold air even, right, still it is a drying. But what is the most stringent criteria? Finally, we must have a dried solid. Even if your feed is solution or a slurry, finally you must have a product stream which is the dried solid, and additionally there will be a solvent vapor, right. Mostly it will be entrained in this drying medium or drying medium rather. Right, or drying gas, let us say it is getting complicated, let us say it is drying gas itself. Okay. Now, you see there are several examples in chemical process or in general process industry, right. Different types of process industries have got examples, like we can dry the leather, okay. In leather industry we can dry the soap bars before final packaging, we can dry sugar, we can dry the different types of organic pigments, organic material, foodstuffs, right. And these different chemicals like sodium, ammonium salt, this sodium sulfate, then drying this table salt. So, different types of pharmaceuticals products like capsules and all, okay. So, these all are to be dried before the final packaging, okay. And the technically what we refer as drying, you must note that we must have used a drying medium. We can use any sort of feed, it may be solid, it may be liquid, or it may be this thick slurry, it may be a solution, but finally we should have a dried solid product. So, it is in a term, it is a solid liquid separation, and a case of simultaneous heat and mass transfer, just like this humidification, very similar to humidification, right. But in humidification we have liquid and air, and that is also a case of simultaneous heat and mass transfer, but their primary purpose was to cool a huge amount of hot water. But here our objective is to remove moisture. There the moisture removal was primarily intended in humidification to cool this feed stream, that is liquid water. But here that is not our primary objective. We have to remove moisture from the feed, and that is the solid, it may be liquid, it may be slurry, whatever it is, and finally converting it into a vapor phase and a liquid phase, right. Oh, sorry, a solid phase, vapor phase and a solid phase. So, you see that you may think that okay, I am concentrating this milk in order to get a condensed milk. So, we are removing this water, so that is also drying. No, technically it is not drying, technically it is evaporation, because the final product is not a solid. But if I simply charge this diluted milk in a spray dryer, that is done in a spray dryer, a special kind of continuous dryer which is suitable for dilute solutions and slurries. So, if I spray it to generate powdered milk, then it is a drying process. Now, industrially we often refer the word drying for different other purposes, right, which are not technically drying, like drying of air, okay. So, keeping the or just allowing the air to flow through a bed of silica gel, that is adsorption, it is not drying. We can dry this, we can dry benzene also. Before chlorination we have to dry it. Dry it means we have to remove the moistures, That's also called drying industrially, but technically it is not a drying. So benzene is to be removed from this dissolved, sparingly dissolved water through a distillation process. So similarly, we can dry the natural gas by keeping a suitable solvent, or by using a suitable solvent, and we remove here, we remove this water from this natural gas, right, before further processing. That we also call drying of natural gas, but technically it is not a drying process. So drying technically must refer as a process where we have any sort of feed, but finally my product will be a solid, right, a dried solid with reduced water content. So with that basic understanding of this drying process, let's think that what are the mechanisms. Particularly, we will not discuss about, just right now we will not discuss about slurry or solution, we will consider a wet solid. So mechanism, what is a mechanism? See, I have a solid block which is wet, and we have a drying medium or a gas flowing over that block. So you see, initially if the solid is heavily wet, there will be a film of water. So the film, from that film it starts evaporating. Okay. So this evaporation actually will do what? This evaporation will take up the latent heat from the block itself. So the temperature of the solid Ts and temperature of the gas Tg. So at equilibrium, this Tg is greater than Ts. Okay. Why? Because there will be heat transfer, or rather we should say it is the latent, that is the direction of latent heat transfer. So that must be balanced by equivalent amount of sensible heat transfer. Right. So there will be sensible heat transfer in the opposite direction and latent heat transfer in this direction from the solid to this drying medium, and as a consequence an equilibrium, and these two rates will be equal at equilibrium. Right, where there is no further change of this moisture content of the solid, neither there is any change of this temperature. So you see, that's the primary way of this drying. So latent heat transfer is always facilitated by mass transfer. So you can understand that it is a combined or simultaneous case of heat and mass transfer. Next, you see that what are the steps? When this film dried up, first these patches, dry spots or patches will appear on this external surface of the solid. And if we continue further, still that will be also dried up. Next, we will have, after initial state, when the external film of liquid completely vanishes, we have internal movement of moisture. Right. So this internal movement means now the solid is dried up. However, there are capillaries, macrocapillaries and associated microcapillaries, which are the cracks. Right. So you see that liquid from this core region of the solid will be transported to this external surface. So how it will be transported? What are the mechanism of transport? The first we have capillary movement, because this is driven by surface tension or interfacial tension. Next, liquid diffusion, through this capillary, it is obvious. Say the drying may be taking place from here over a plane which is internal to that solid surface. So, there we have the generation of vapor and we can have the vapor diffusion. And lastly, it is pressurization. What is that? See, when we expose a solid, right, we expose a solid to a drying this gas and this external liquid film vanishes, then there are possibilities that the solid will shrink, right. A compressive force will be generated which is directed from outside to inside, and as a consequence that internal these regions of the solids, which is a wide this porous structure, right, fitted with these capillaries and all. So, what will happen that as we are having a squeezing effect, a compressing effect on the surface of the solid, because of that pressure, right, the liquid will try to move out. Just like if I squeeze a wet cloth, what will happen? The water will spill out. So, the same mechanism is the transport based on pressurization, but that is not universal, because if the solid is not having any change, high elastic, right, it is not going to deform because of drying. So, then there will be no pressurization effect and we will have this capillary movement, liquid diffusion, vapor diffusion, etc., as the governing mechanism, transport mechanism for drying. Whereas, pressurization is very probable where the solid shrinks, right, upon drying. So, in order to understand that overall process, first we have to go for understanding what is called drying equilibrium. Right. What is that? See, again we have a block of wet solid, we have this drying gas which has got a partial pressure Pa, right, partial pressure of water, it is Pa. So, partial pressure of water vapor. Right. Now, what happens? The moisture in the solid will also generate a vapor pressure at the surface. So, that is, let us say it is PAS, right. So, this is the partial pressure or vapor pressure generated by solid moisture. Vapor pressure generated by the solid moisture. Now, once these two, right, they are same, and that vapor pressure, what is the vapor pressure being generated by the solid? That depends on what? This PAS, that depends on temperature, depends on this moisture content of the solid, depends on this temperature, and depends on the physicochemical properties of the solid. That is its structure or the distribution of the cracks, then the chemical nature, that how hygroscopic it is, or more precisely that what is the nature of interactions of the solid constituent chemical with water, right. So, there are different issues which will govern this vapor pressure generated by this moisture content in the solid. So, when these two, like the vapor pressure generated by the solid and the partial pressure of water vapor in the gas, when these two are equal, right, when these two are equal, the drying will cease. Okay? So, for a given temperature and for a specific type of solid, this PA, so we can write for a given temperature and for a specific type of solid, the vapor pressure generated by the moisture contained in the solid is a function of x only, where x is the moisture content. Moisture content of the solid, right, and it will attain the equality with PA. And alternatively, see, as it is difficult, practically impossible to determine the numerical expressions of PA, so it's not so easy as a function of x, because that depends on the structure of cracks, which is highly random, right. Its interactions, the molecular scale interactions of the solid constituent molecules, solid molecules with that of water. So, it is not so easy to formulate this sort of mathematical correlation. So, how we bypass that exact mathematical evaluation? We can go for plotting the experimental data of this PA by PAS. PAS is not that PAS, or rather let us say PSAT, that is the relative humidity of this drying gas with X, right, when the drying ceases and no further change of X is taking place, and that is called the equilibrium plot or drying equilibrium curve. So, what is that? Let us see. So, it is the drying equilibrium curve. Here this is X, and how the moisture content is written generally in dry basis. So, this is kg of moisture per kg of dry solid, right, and here we are plotting PA by PSAT, which is the saturation pressure. At the operating temperature. So, this is a curve for a fixed temperature. As we increase the temperature, the drying curve is going to change. So, it is from 0 to 1. So, it is basically the relative humidity term, RH or HR, right. Now, you see the nature of the curve is somewhat like this. It may be like this and it may be like this as well. So, just like here we can have the plot of zinc oxide, the typical example, this may be the leaf tobacco, this is wood, etc. Right. Now, you see this a point, just a point on this plot of wood is like when this is the equilibrium moisture content, let us write x term. So, this is 0.1 and here it is 0.6, let us say 0.1 is the exact data, 0.1 and 0.6 for wood, right. So, this is the kg of moisture per kg of dry solid, or we should write the kg of moisture at equilibrium, right. So, how to generate this sort of curve? We will actually start working with wood. So, wood will give a definite moisture content, we can change it, but let us fix it for the time being. Let us say the wood has got a specific x value, that is the initial moisture content, right, and we expose the wood block in a flow of this here with a given relative humidity, say it is 0.1, right. So, wood will naturally lose the moisture, will attain some definite x star value. So, we will mark that point. Next again we will repeat that experiment with say this another this RH. Okay. So, in this way we will go on generating these plots or these points, and if we join them smoothly by a curve, we will get the drying equilibrium plot. So, you see that after some specific value of X star, it saturates to this threshold value which corresponds to RH equal to 1. Let us mark the point as B. And what is the significance of this point? You see that we have started with, let us say an experiment, we have started with Xi is equal to say it is 0.3, right, it is somewhere here. Okay. So, at this specific moisture content, if I expose it to a air stream having a relative saturation of this relative humidity of 0.6, what will happen? The wood will progressively lose the moisture, but initially we have to note that when the moisture content is 0.3, definitely there will be layers of water existing over the external surface of wood, right, which is not being held tightly, right, with wood by means of physicochemical interactions with wood fibers, right, because the film, its thickness is in the order of millimeter, whereas the interfacial force that is typical, this DLVO, it is called the DLVO force, it is a combination of van der Waals force and electric double layer force, right, which acts between the surface and these ions. So, this electric force and the double layer force, that scale is in the order of nanometer. It vanishes completely at around 10 nanometer, right, for most of the surfaces. So, what will happen that the liquid here, whenever we are having an external film, it is not having a physicochemical interactions with the wood fibers, right, there is no intermolecular forces. So, it is rather free. Okay. So, definitely when we expose it to a saturation, to a air stream with saturation humidity 0.6, the wood will go on losing water. So, finally, this external film will vanish, right. So, once the external film vanishes, next this external film vanishes. Next, it releasing moisture from the capillaries, and capillaries are being supplied, the macro capillaries are being supplied by micro cracks and micro capillaries. So, micro cracks and micro capillaries may have got a dimension in the order of nanometer, where these intermolecular forces are quite prominent, and even in macro capillary size there are intermolecular forces close to the wall, right. So, as a consequence, what we can say that here this if I expose it to just if I expose wood, if we think in the reverse direction, this is a wood has got a moisture content, say it is 0.05, right, somewhere here, and we expose it to saturation value, to a drying medium which has got a relative saturation equal to 1. What will happen? It will acquire moisture upon adsorption and ultimately attains equilibrium at this point B. So, when the internal, all the capillaries of the wood is fulfilled with its capacity of holding water, right, but there is no external film. So, that much amount of water which can fill the internal these crevices, cracks, capillaries, etc., these are basically having a interaction, intermolecular interactions with the wood fibers, right, and that is why these amount of moisture up to the point B is called bound moisture. Okay. So, this is referred as bound moisture. And definitely the PAS, which is the vapor pressure generated by the solid moisture, is just equal to PASat, right. When the solid is just having the bound moisture, the PAS will just attain the value of PASat, and here also the value is always same, PAS is equal to PSAT. But here in this region, PAS is less than PSAT, otherwise it will not dry. Okay. So, bound moisture is a specific moisture content below which the vapor pressure exerted by the moisture of the solid is always less than the saturation vapor pressure, right. Whereas, above and over this bound moisture, what we refer? We refer this moisture content above and over the bound moisture as unbound moisture. Just the name, as the name suggests, that here if we have an external film, the intermolecular interactions between the water which is in the film with wood fibers is practically null and void, right. There is no specific interaction, as the thickness of the film is in the order of millimeter. So, we will call that moisture as unbound moisture. So, physically when we have an external film, that is the unbound moisture, and the moisture content whatever is internal to that wood matrix, it is the bound moisture, because it has got those moistures has got strong physical or physicochemical interactions with these wood fibers, right. So, that is the idea of bound moisture and unbound moisture. So, bound moisture, you see, we can define that it refers to the moisture contained by the substance which exerts equilibrium vapor pressure, that is, a vapor pressure exerted by the solid less than that of pure liquid at the same temperature. So, already we have defined it. So, bound moisture up to the bound moisture, this is the total bound moisture. So, if it is only having bound moisture, the vapor pressure exerted by this solid moisture or this moisture content of that solid, it is always less than the saturation vapor pressure of that pure liquid. Whereas, in the case of unbound moisture, as we have a film, it will always exert. See, if we have a film here, here at the surface, we will have the PAS is equal to PSAT, right, always equal to PSAT, because at the surface of water, whatever thin it is, but if it is an external film or the surface or this layer of liquid, it will always exert a vapor pressure of the pure liquid. So, bound moisture and unbound moisture, that we have got an idea, and additionally we have told about this equilibrium curve. Now, it may be questioned that how you have generated the equilibrium curve, whether you have taken initially the what is your feed in this experiment, whether you have taken a wet solid or you have started with a bone dry solid, right. So, first one and second one both are possible to generate the equilibrium curve, and the first one where we have taken a wet solid, it is a desorption experiment, right, where water is being released from that solid, and the second one where we have taken the absolutely dry solid, a bone dry solid. So, it is absorbing moisture from this gas stream, and it is basically an adsorption experiment. So, there exists hysteresis, or it is called drying hysteresis. So, if this is the equilibrium curve for adsorption experiment, it moves like this. This will be the equilibrium curve for desorption experiment. Right, it moves like this. So, this is RH and this is X star. So, point is why there is an hysteresis. You see, for that we have to go for physical chemistry and the associated structure. If I think that this is capillary in the solid, here we have different functional groups on the surface, right. So, some functional groups are having positive, negative, then positive, negative, etc. Now, if I am going by desorption experiment, this groups, say this is a group, right, with a charge of negative delta, it is always having a shell of hydration. It is surrounded by water molecule, right, and these water molecules are having strong interactions with this polar head group or polar functional surface functional groups. Okay. Now, if, so they are saturated and self-contained, but if it is an adsorption experiment where we have only these groups with negative charge, maybe here a positive charge, maybe here a negative charge, etc. So, there will be repulsions between the two adjacent groups if the polarities are same, and they will attract each other. There will be stretching of these bonds if the polarities are different, right? And because of that stretching, the collective effect of that stretching or this capillary morphology will be that the wall of that capillary will be stretched and its total void volume may change. Okay. So, as a consequence, but here it is not going to change for in case of desorption experiment, because in desorption experiment always we are started with a solid which is containing unbound moisture. There is a film on this external surface, right? We can start always with that. So, these groups, these surface functional groups are hydrated in the beginning of experiment, and its water holding capacity may be higher, may be lower, or at least we can say it is different from that of bone dry solid, because the capillary morphology is different because of this hydration effect, right? And that is why we have hysteresis. That is a crude physicochemical kind of reasoning behind this drying hysteresis. Okay? So, we have now some definitions, like as I have stated that we have the moisture content already we have defined. Okay, let me write. The moisture content of the solid already we have defined. So, once we have defined the moisture content, and generally we use this dry basis. So, it is kg of moisture per kg of this dry solid, right. So, we have the equilibrium moisture X star. What is the definition? The moisture content of the substance when at equilibrium with a given partial pressure of the vapor, right. The moisture content, so this is simply the moisture content of the solid in equilibrium with the drying gas having a fixed relative humidity, right. So, next is the bound moisture. So, the moisture content of the solid which will exert a vapor pressure always less than the saturation pressure of pure liquid at the same temperature is bound moisture, right. Above and over this we have unbound moisture. So, this is the moisture content. This refer to the moisture content by a substance which exerts equilibrium vapor pressure equal to that of. So, here for this moisture content PAS is equal to PA sat, right. And the free moisture, this moisture content above and over the equilibrium moisture content, right. So, you see that diagrammatically we can represent it like this. Right. So, this is the RH, this is 1, this is 0 and this is x. So, somewhere here for a specific material, as we have seen that this is x star. So, this is equilibrium, right, and let us say this is xi. Okay. So, that means this is free moisture content. Okay. And here up to this it is a bound moisture and this much is unbound moisture. So, that is about the basic introduction of drying regarding its equilibrium plot, properties and different drying mechanism. So, in the next session we are going to discuss about the drying test and different types of industrial dryer what we use today. Thank you.